So this is Hpas 2019 main paper 2, question number 2 and 3. So in the question number 2a, find the transformation which maps the semi-infinite strip of width pi bounded by the lines v is equal to 0, v is equal to pi and u is equal to 0 into upper half of z plane. So in this case, we can use a conformal mapping to map the semi-strip of width pi bounded by lines v is equal to 0, v is equal to pi and u is equal to 0 into the upper half of z plane. In the first, what we are going to do, we are going to map the strip onto the unit strip in the y plane using the transformation. So this is the transformation which we are going to use, and this maps a line v equal to 0 onto the real axis of w plane, the line v is equal to pi onto the imaginary axis in the w plane, and line u is equal to 0 onto the line of imaginary of w 1 upon pi log pi upon z. So we have already found out the mapping. It means the line v equal to 0 will be as a real axis of w plane, v is equal to pi onto the imaginary axis, and for u is equal to 0 we are going to get a line this. So the strip is mapped into the horizontal strip which lies between the interval from 0 to 1 of the imaginary part w. Now we can map the unit strip into the w plane onto the upper half of z plane. This is the second part of the question using the transformation z is equal to 1 plus w, 1 minus w. So according to the question, this maps the real axis of w plane onto the unit circle in the z plane and upper half of w plane onto the upper half of the z plane. So combining both the transformation, we get the mapping as z is equal to 1 plus 1 upon pi log z minus I pi divided by z, and 1 minus 1 upon pi log z minus I pi divided by z. So it means this maps the semi-infinite, the strip of width pi bounded by the lines v is equal to 0, v is equal to pi and u is equal to 0 into the upper half of the z plane. So this is the first part. In the question number 2b, we are going to evaluate in the close where C is the circle which is defined by z minus 1 equal to 1. So in this case, we can evaluate the contour integral using the residual theorem. We are going to use the residual theorem. So since the integrate has singularities at z is equal to plus minus 1, and this singularity lies inside the contour C, so we can use the integral using the residues of integrand as at this singularity. It means we are going to find out the singularities, or we can say basically the solution using the value z is equal to plus minus of 1. So we are going to first of all factorize the denominator z square minus 1, that will equal to z minus 1 multiplied by z plus 1. The integrand was given as 3z square plus z divided by z square plus 1. So it will be further sorted as we divided the denominator into two parts, z minus 1 and z plus 1. So this will equal 3z divided by z plus 1 plus 2z z minus 1. Now we are going to find out the residue of this, the first term at z is equal to minus 1. So at z is equal to minus 1, the residue 3z z plus 1 comma the value of z, and this is the first function. It is given as limit z tends to minus 1 z plus 1 and 3z z plus 1. So this will be equal to 3 of z, minus 3. The residue of the second term at z equal to 1, so this will be value of z, this is residue, and this is our second term. So we get z is equal to z limit z minus z to 1 z minus 1 to z z minus 1. So this will be equal to 2. We already found out what will be the value of the residue. So as per residue theorem, with the integral this unit circle 3z square plus z square minus 1 to 2z, so we already found out what is the value of residue first part and residue of second part, that is equal to 2 pi I. Value of this is minus 3 and that is equal to 2. So ultimately this will be equal to minus 1. So minus 1 into 2 pi I will be giving us minus 2 pi I. So therefore the value of the given contour integral is minus 2 pi I. So this completes the second question. The question number 3 has 3 parts, A, B, and C. So in the first part, show that a cyclic group is necessarily abelian. Show by example that converse may not always be true. So basically this is based on few definitions. A cyclic group is necessarily abelian. This can be shown as follow. We consider let G be a cyclic group with the generator G. Capital G is a cyclic group with a generator small g. Then by the definition of cyclic group, we can say that every element, it means if G has number of elements as H, so we can write that H will be equal to generator G raised to power K, where K is any integer. So let us now consider two elements. H of 1 will be equal to G of A and H of 2 is equal to G of B of G. So we need to show that product of H1 H2 is equal to H2 H1. So here we simply substitute the value of H1 H2. So we get G A, G raised to power A multiplied with G raised to power B, and this is basically some of the, we can see exponent properties here, and reverse we are also true. And we additionally know that it is commutative in nature, that is A plus B is equal to B plus A. So we get the first part is true. G raised to power A plus B is equal to G raised to power B plus A. So we can say that H1 multiplied by H2 is equal to H2 multiplied by H1. So it means this operation is abelian. So any cyclic group is necessarily abelian since it can be generated by a single element and the product of powers that generator is abelian. This is the first. Now we are going to prove that the converse might not be true. That is, abelian group need not be cyclic. So we took one example. Example is stated that cyclic group is the group of integers z under the addition. So z is abelian since addition of integer is commutative. We already proved that. However, z is not cyclic since no integer that can generate all the integer under addition. For any integer n, the set of integers generated by n under addition will not cover all the integers. So it means Z is an abelian group, but that is not cyclic, showing that the converse not necessarily true in all the respects. So this is question number B of third question. So this is also basically a pure theoretical one. Examine if there exists a one-to-one correspondence between right and left coset of H in G if H is any subgroup of G. We are going to examine the property. So let us examine this group problem by step. So we are given that a group G and there is subgroup H which is a subgroup of G. Now we want to determine if there is one-to-one correspondence between the right cosets of H in G and left cosets of H in G. So first we are going to find out what about the right cosets of H of G. Right cosets of H in G is in the form of HG, where G is any element of capital G. So it means it contains all the elements in the form H small h multiplied by small g, where H is any element of capital H. Now we find out the left coset. So a left coset of H in G is in the form of G into H. So that is this is the right coset. Right means H multiplied by small h G, and left means small g multiplied by H, where G is any element of capital G. And similarly, it contains all the elements in the form G into H. So because of the left and right, the position of G and H is going to change, where H is any element of capital H. So number of right cosets of H, capital H in capital G is given by a big bracket from G to H. The index, basically it is called the index of H in G. And whereas in left it is called as the index of is also G to H the index of H in G. This shows that there are equal number of right cosets and left cosets. So in summary, we can say that for an arbitrary subgroup H of an arbitrary group G, there does not necessarily exist one-to-one correspondence between left and right cosets of H in G. Now this is the third part of the third question, which states that if F is such that which G corresponds to G prime is a homomorphism, then image of F is a subgroup of G prime. So we are going to prove this part. So what we consider that let G such that G prime be homomorphism, we need to show that the image I am F of G satisfies the subgroup criteria. So it has some three properties. If we satisfy all these properties, we can just prove it. First property is closure under operation. Let A and B belongs to image function F, then A is equal to F of X and B is equal to F of Y, such that X comma Y belongs to a G function. Since F is homomorphism, we have F of X multiplied by F of Y is equal to F of XY belongs to image function F. Therefore, image function F is a closed under the operation G prime. Next is identity element. Since F is homomorphism, we have F e to the base capital G is equal to e to the G prime, where EG and EG prime are the identity elements of G and G prime respectively. So we can say that EG prime belongs to also the image function F. Next is the inverse element. So in this case, we say that let A is equal to F of X belongs to image function F. Since F is homomorphism, we have F X inverse is equal to F X whole inverse belongs to image function F. So therefore, for every A belongs to image function F, its inverse is also in image function F. This shows that image function F satisfies the criteria to be in a subgroup of G prime. So these are the three criteria, and all these criteria are being satisfied. So if we conclude that G belongs to G prime is a homomorphism, then image function F is a subgroup of G prime. Thank you.